This module introduces positive displacement motors. These motors convert hydraulic energy from the drilling fluid into torque at the bit, enabling independent rotation of the bit from the drill string. We will explore their design, applications, selection criteria, and limitations. Understanding PDM fundamentals is essential for efficient, cost-effective, and reliable drilling operations. This module will be broken into 3 sub-modules. This is sub-module 1 of 3. At the end of this module, you should be able to achieve several learning outcomes. First, you will be able to explain the differences between a steerable PDM and a PDM used in combination with a bent sub. You will also become familiar with types of high torque motors, an important category for challenging formations where extra power is needed. Another objective is to understand bit and motor selection criteria and how these choices impact drilling performance. We will also address the directional tendencies of steerable motors, helping you predict and manage well path outcomes. Importantly, you will learn to balance operational costs with directional objectives, developing the ability to identify which solutions are most economical. Finally, we will review common PDM failure modes, explore the phenomenon of motor stalls, and discuss corrective actions. These objectives provide both technical knowledge and practical guidance, preparing you to apply these principles in real-world operations. Keep these goals in mind as we progress through each section, as they frame the content and serve as benchmarks for your understanding. In this sub-module 1, we will focus on the first 2 objectives. The aim of a mud motor is to convert the hydraulic power of the mud systems into mechanical power that will turn the bit. It can be seen that as the pressure drop increases, the hydraulic power also increases as long as the flow remains constant. The efficiency of the system is calculated relative to how efficiently the motor does this conversion. PDMs are a lot more efficient than turbines at converting hydraulic HP to mechanical HP. The key to steerable motors lies in 2 formulas, hydraulic power and mechanical power. First, hydraulic power is calculated as flow rate multiplied by differential pressure. This value represents the energy delivered by drilling fluid. Then, we substitute hydraulic power into the mechanical power formula to determine torque output at the bit. Torque is critical because it directly dictates drilling efficiency and bit performance. The relationship between fluid hydraulics and mechanical torque explains why PDMs are so effective in directional wells. By managing flow and pressure parameters correctly, engineers ensure optimal motor output, improved build rates, and reliable hole cleaning performance. At its core, the PDM consists of 3 main sections: the power section, the transmission section, and the bearing assembly. The power section is where hydraulic energy is converted into torque using the rotor and stator combination. The transmission section transfers this torque through universal joints or flex shafts, ensuring that the eccentric rotor motion is translated into smooth rotation. The bearing assembly then supports weight on bit and transmits torque to the drill bit while withstanding axial and radial loads. The stator is typically elastomer lined, bonded into a steel housing, while the rotor is a metallic component with a helical profile. Materials and coatings must be carefully selected to resist wear, corrosion, and temperature degradation. This basic design allows the motor to function under a wide range of downhole environments, though each component has its own vulnerabilities. For example, elastomers can swell in certain fluids or high temperatures, and bearings can fail if overloaded. Recognizing these design fundamentals enables drillers to optimize motor performance and longevity. The power section is the heart of the motor, and its design dictates performance characteristics. It consists of the rotor and stator arranged helically. The rotor always has 1 fewer lobe than the stator, creating sealed cavities that progress along the length of the tool as drilling fluid is pumped through. Pressure differentials across these cavities generate torque and cause the rotor to rotate. The geometry of the lobes influences torque and speed. More lobes typically give higher torque but lower rotational speed, while fewer lobes provide higher speed but less torque. This trade-off is crucial in motor selection. For example, drilling hard formations often requires high torque motors, whereas softer formations may benefit from higher speed. The elastomer lining inside the stator must also be chosen carefully, considering mud type, solids content, and downhole temperature. Any mismatch between fluid properties and elastomer performance can lead to premature failure. Thus, power section design balances lobe geometry, elastomer properties, and fluid compatibility to achieve reliable performance in demanding drilling conditions. This video should help in visualizing how the rotor rotates within the stator. Next is a video by Dynadrill explaining how their motors work.
Dynadrill is a premier design and manufacturer of downhole motor equipment for the oil and gas industry. With our top-of-the-line facilities, we create unrivaled products that outperform our competition. For over 60 years, Dynadrill has been recognized as a technological leader and continues to create new products that are transforming the downhole drilling process. Dynadrill's power section, which includes the stator, elastomer, and rotor, are built for endurance. To ensure it can handle long production hours and extreme drilling applications, Dynadrill extensively tests the power section with our 1500 horsepower dynamometer. The stator has a uniquely formed elastomer bonded inside the stator housing that forms a sealed fit, which converts pressure and flow of drilling fluid to torque and rotation. The bonded stator and elastomer are combined with a highly polished rotor, with one less lobe than the stator. Dynadrill rotors are made out of stainless steel and can be carbide coated or chrome plated to maximize protection against wear and erosion. The stator, elastomer, and rotor work together in unison to create a spiral motion that minimizes friction and improves efficiency. The bearing assembly transfers the bit load to the drill string and is protected with our patented Matrix 3 coating to provide exceptional resistance to metal impact, wear, corrosion, and mechanical fatigue. Our Matrix 3 bearings are made out of an incredibly hard composite and are metallurgically fused to the base metal to create an inseparable bond. Above the motor is the MWD or LWD. The MWD measures the drill string orientation in real time, and the LWD logs the formation of the properties being drilled. Dynadrill understands that every customer has different needs, so we custom manufacture these parts to the customer's exact specifications. Manufacturing these components requires precision machining, a well-known service offered by Dynadrill. Both the power sections and radial bearings are specialties of Dynadrill. When dealing with downhole drilling, consider the importance of quality, reliability, and productivity. All Dynadrill products are vigorously tested and manufactured with the understanding that when dealing with wear, corrosion, and friction, choose products with power that lasts. Dynadrill. Talk to a sales rep to determine the best product and solution that fits your downhole drilling application.
The stator is a critical part of the PDM, serving as the stationary component of the power section. It consists of a steel housing with elastomer bonded to the inside surface. This elastomer forms the sealing surface against which the rotor turns. Several elastomer types are available to suit different drilling environments. For example, RM100 elastomer is suitable for water-based and oil-based muds under moderate conditions, while RM145 is designed for higher oil-based mud temperatures exceeding 280 degrees Fahrenheit. For extreme temperatures above 300 degrees Fahrenheit, RM245 is often selected. Elastomers degrade when exposed to incompatible fluids or temperatures beyond their design, so careful selection is critical. Stator housings are relatively thin-walled, making them susceptible to corrosion, especially at threaded connections. Manufacturers have also developed contoured stators, which provide more even elastomer thickness compared to traditional designs, improving durability. Understanding stator limitations and choices helps drilling engineers minimize motor failures and extend downhole performance in challenging wells. SLB acquired a motor company called Dyno Drill. Its equivalent stator to RM100 is NBR1A, of which the performance stator is HR series, which stands for hard rubber. The RM series was developed by a company called Robbins and Myers, which at one point was an independent company supplying stator rubbers to the industry. Robbins and Myers was acquired by NOV, and although they still provide for the industry, they prioritize products internally. Next is a video from Dynadrill on the manufacturing of their power sections.
Welcome to Dynadrill. Please join us as we tour one of our top-of-the-line facilities. On this 328,000 square feet facility in Katy, Texas, Dynadrill produces a broad range of motor power sections, rotors, and stators that are designed and manufactured to withstand the most demanding drilling applications. Dynadrill is able to deliver a complete, newly designed power section from drawing to the field in the shortest lead time on the market. In its activity peak in 2014, the facility manufactured more than 2,900 rotors and 25,000 relines under the most rigorous quality standards in the industry. Dynadrill rotors are produced through high-precision, computer-numerical control CNC machining. We maintain the industry's latest and most sophisticated milling equipment to precisely contour rotors of various lengths. After machining, the rotors are carbide-coated or chrome-plated to maximize protection against wear and erosion. Dynadrill verifies every rotor profile using a coordinate measuring machine, CMM, and proprietary contour measurement software. A crucial Dynadrill service offering is stator relines. Experienced personnel allow Dynadrill to address reline needs in a productive and highly cost-effective manner. Dynadrill can reduce the time needed for the reline process by days through our attention to detail and proven efficiency. Stators in need of relines are received in the facility and go to our CNC induction process to ensure all organic material is eliminated. The tubes are then transported by conveyor system to the stamping operation. There, each tube is identified with the internal tracking number and customer serial number for as-built records and full traceability control. We perform a receiving inspection to assess the incoming condition of the tubes and take critical measurements of the tube to get a precise fit for our mold tooling. After inspection, the tubes go to a supermarket can van that allows the planning team to schedule a single piece flow to coordinate core mold use and maximize customer deliveries. Directly after surface prep, precise application of cutting-edge adhesive compounds provides a strong chemical bond between the stator and elastomer. The stator is assembled with the molding core using custom-fit tooling based on measurements taken in the prep cell. Critical assembly data is recorded to verify conformance to standards. The stator is then injected with elastomer, specifically chosen based on drilling application. All injection parameters are set per specification based on the elastomer in use. After injection, the stator is cured with manufacturing precision. Autoclaves deliver precise, CNC-delivered curing cycle times and temperatures tuned to the different elastomers and stator sizes. Curing cycle records are maintained on each and every stator. A quench cycle is performed with procedural times and temperatures to complete the cure. Then the stator product and molding core is disassembled. The core is again recirculated back to the assembly operation to be used again in the next scheduled product. The reline stator product is rubber profile finished at the cutback operation. Skilled craftsman operators use proven technology to ensure the product meets specified dimensions with regard to form, fit, and functionality at the connections. After cutback, the product is vigorously subjected to an all-points rubber inspection process to assure and record the built-in quality of the stator, and that the stator meets all reline manufacturing specifications and is so certified. At final inspection, Dynadrill verifies the integrity of the rubber's bond to the interior of the tube, ensure there are no imperfections in the rubber profile, and take key measurements of the rubber to ensure proper fit with the rotor. All of these as-built records are reviewed and stored digitally in our proprietary computer database. The tube is then certified and delivered to the customer. Every new Dynadrill power section design is tested and proven on a dynamometer. Our dynamometer is the largest in the industry and ensures superior quality control to sustain long production hours and unrivaled mud motor performance in extreme drilling applications. Through a regimen of continuous research and sophisticated testing protocols, Dynadrill provides the latest in elastomer technology. Our state-of-the-art elastomer lab has developed improved stator rubber compounds and continues to produce the most technologically advanced downhole motor equipment in the industry. Dynadrill's ultra-modern plant and computerized engineering capabilities merge craftsmanship, sophisticated machining tools, and quality assurance technologies to produce outstanding performance power sections. Quality, reliability, and productivity. That is Dynadrill.
There are two major stator designs. Regular stators are molded around a cylindrical blank, resulting in uneven elastomer thickness. These variations can create weak spots, reducing life in high temperature or abrasive conditions. To address this, the industry developed contoured stators, which maintain even elastomer thickness. Examples include extreme motors, even rubber thickness ERT, and power edge technologies. These designs enhance durability, reduce heat buildup, and improve torque consistency. The selection of stator type is critical in matching motor performance with drilling environment. In abrasive or high torque applications, contoured stators typically offer better life and performance. For standard wells, conventional stators may be sufficient and more economical. The diagram illustrates differences between regular and contoured stators. Notice how the regular stator shows uneven elastomer thickness, whereas the contoured stator maintains consistent thickness throughout. This evenness reduces stress concentrations and improves heat dissipation, which directly enhances motor reliability. Even rubber thickness ERT technology represents a major step forward in stator design. Unlike conventional stators, which have varying elastomer thickness, ERT stators provide uniform thickness along the entire housing. This results in lower localized stress, reduced hysteresis heating, and extended stator life. For drilling operations, this means improved motor reliability and fewer trips for motor replacement. Field studies have shown significant performance improvements in demanding wells, especially where downhole temperatures are high or mud systems are aggressive. While ERT stators may carry a higher initial cost, the reduction in failure risk and associated non-productive time often makes them more economical in the long run. For drilling engineers, the ERT option provides an attractive balance between performance, durability, and cost-effectiveness. Although there are many advantages to the ERT stator, the main downside is a significant increase in the pressure drop. This can be a limiter to many rigs, which are limited by pressure, especially in deep wells or long tangent sections. This slide compares the performance of conventional power sections with the even rubber thickness motor design, or ERT. Specifically, we're looking at a 9 5/8 inch motor across 3 configurations. On the chart, we have 3 sets of data: the 962 XP, the 962 GT, and the 962 Power Pack ERT. Each shows length, torque, and horsepower. Starting with the 962 XP, this motor has a length of 218 inches, delivers 18,000 foot-pounds of torque, and produces 280 horsepower. The 962 GT is slightly longer at 240 inches with higher torque at 24,000 foot-pounds and a power output of 342 horsepower. Now compare those to the 962 Power Pack with ERT technology. At the same length of 240 inches, this motor delivers 34,400 foot-pounds of torque and 590 horsepower, significantly higher than both conventional designs. The key takeaway here is that the ERT design not only matches conventional motors in size, but also provides a step change in torque and power. This results in improved drilling efficiency, enhanced performance in demanding formations, and a more robust motor for high torque applications. Rotor coatings play a crucial role in motor reliability and longevity. The rotor operates in close contact with the stator elastomer, and its surface condition affects wear, corrosion, and torque generation. Several coating options exist. Unplated rotors are inexpensive and adaptable, but prone to corrosion and erosion. Chrome-plated rotors are widely used due to low cost and ease of recoating, but they are unsuitable in high chloride environments. Tungsten carbide offers high resistance to corrosion and erosion, though it is expensive and difficult to retrieve if lost in hole. Ceramic coatings are also costly, but excel in high temperature, high pressure conditions. Choosing the right coating depends on mud type, downhole chemistry, and economics. Engineers must balance cost, resilience, and fishing risk. Proper rotor selection can dramatically extend motor life, reduce maintenance, and improve drilling performance, particularly in aggressive or corrosive environments. A nozzle bypasses some of the flow through the center of the rotor, thereby reducing the amount of flow through the power section. As long as the required amount of flow passes through the power section, then the torque and RPM output of the motor will not be affected. However, since the amount of flow bypassed is directly proportional to the pressure drop across the power section, it is possible that attempts to drill with high differential pressures will result in starving the power section. This will also result in a lower stall pressure. A rotor nozzle should be used when it is necessary to circulate at flow rates greater than the power section specification. This may be required for hole cleaning purposes in large hole sizes. They are also used in specific applications such as spudding, under-reaming, or hole opening. It is relatively uncommon to run a rotor nozzle, which can be mitigated with correct engineering for the section to be drilled. Selecting the right power section requires consideration of multiple interrelated factors. The type of bit and formation determines torque and speed requirements. Downhole temperature and drilling fluid composition dictate which elastomer and rotor coating will survive. High solids content accelerates wear, so designs with improved durability are preferable. Build rates must also be considered. Motors with more lobes deliver higher torque for harder formations, while those with fewer lobes provide greater speed. Hydraulics requirements, including hole cleaning and nozzle bypassing, also influence the decision. Finally, the type of guidance system, such as MWD or rotary steerable, may restrict available power sections. Engineers must integrate all these criteria to balance cost, reliability, and performance. Poor selection can lead to motor failures, unplanned trips, and higher well costs, while careful selection ensures efficiency and reliability. Now that we've covered the content, let's revisit the module objectives. We began by distinguishing between steerable PDMs and PDM/bent sub combinations, highlighting their respective advantages in directional drilling. We explored high torque motors and reviewed bit and motor selection principles. In the next sub-module, we will examine directional tendencies and how these influence trajectory control. We will also discuss operational costs in relation to directional objectives, giving you tools to evaluate economic trade-offs. In addition, we reviewed common PDM failure modes, including elastomer degradation, bearing wear, and motor stalls. Thank you for your participation. Please proceed to complete the quiz.